Okay, so we are talking about Bellman-Ford algorithm. So today we will discuss the correctness of the algorithm. So what is the Bellman-Ford algorithm? It is to find the single source shortest path. Single source shortest path. So we discussed this algorithm in the last class, but just to recap. So the input is a graph, directed graph, and a weight function, and here we have no restriction of the positive weight. So we are allowing to have the negative weight. So there is a chance of negative cycle, but our algorithm can handle that. And we have a source vertex, which is also another input, and the output will be the delta of s comma v. So this is the weight of the shortest path, from S to, from source to the vertex V. So that means we have a vertex S and we take any other vertex V. So there are many paths from, there could be many paths from this. If there is no shortest path, then we denote delta of S comma V as infinity. So this can happen, either there is no physical path from S to V, or there is a path from S to V, but there is a negative cycle from in that path. In that case, the shortest path will not exist. So this is one of the condition where the shortest path will not exist. So this is for there is no path, one case, and another case, although there is a path between S to V, but there is a negative cycle in the path. So then there will be no shortest path. In that case, we denote this by this. So this is the path P, which is the shortest path. So delta of S comma V is basically weight of the, so minimum weight among, so all the path which is from S to V. So this is the shortest path weight from S to V. So we have to find shortest path from S to any other vertices. So that is the problem. Okay, so let us just recap the Bellman-Ford algorithm, then we will talk about correctness of this. So for Bellman-Ford algorithm, we are just having a initialization step. So this is the pseudocode for this algorithm. We are assigning degree of S to be 0. S is the source vertex, which is the input, and for any other vertex, we are assigning the degree to be infinity, because we have an exploriate, and then okay. So and then for I is equal to 1 to V minus 1 times this outer loop, and we are doing the branch of relaxation. And for each edge under this loop, for each edge UV belongs to E. What we are doing? We take a edge UV, U to V direct edge, and we are checking whether we could relax this vertex or not. So that means this is having a dV, which is the sort of distance estimate from S to that vertex. So now we have, now for this edge we have a new path. We have S somewhere here. So S to this node, this is du, then W UV. So we have a path, now we have a path S to V is like this, du plus W UV. So if this is less than the path we have, then we must relax this. Okay. So this we have to do if dV is greater than du plus W UV. If dV is greater than du plus W UV, then we must relax the a vertex V. Then dV must be relaxed. So, this is the relaxation, this step is the relaxation step. Okay, this is the relaxation step. So, this is 6, 7 and then finally, so this should give us, if there is no negative cycle and then there will be shortest path. So, this should give us the shortest path if there is no negative cycle. Anyway, we will prove the correctness, and after that if there is a negative cycle, then it will keep on relaxing some of the vertices. So, for that we need to have a last checking. So, this is the for each u v belongs to E, we just do this final checking, do if dv is, if v could be further relaxed, then there is a there is a problem, that means the negative cycle exists in the path. Then report negative cycle, that is it. So, this is the pseudocode for Bellman-Ford algorithm. So, for this purpose, in the last class we have taken one example. So, there we have to execute this for v minus 1 times, this outer loop. So, why v minus 1 time, we will discuss this in the correctness, and also we have to do it inner loop is for all the edges. So, what we did, we have edge numbering. So, we are following the same numbering for all the outer loop. Okay. So, we do the edge numbering, then we are following this numbering for, and then we are executing this relaxation step, and finally, when we exhaust, if it is converging, that means there is no negative cycle, and it must converge by this many times, I mean v minus n times. So, let us just talk about the correctness of this algorithm and why it is, why the outer loop is v minus 1 time. Okay, so let us talk about correctness of Bellman-Ford. So, what is this telling? This is in a theorem. If G be a graph, directed graph, which contained no negative cycle, then after Bellman-Ford executes algorithm we have the degree, basically will give us the deltas for all v belongs to v. So, this is the correctness of the Bellman-Ford algorithm. What it is telling? It is telling us if there is no negative cycle in the path in the graph. So, that means the shortest path will exist. Now, if the shortest path will exist, then after execution of the Bellman-Ford for that many time, for v minus 1 time, order of v minus 1 time, it should give us the shortest path weight, and that is basically coming from the degree of each of the vertices. So, that we have to prove, and why v minus 1 time, that we will see soon. Okay. So, how to prove this? Okay. So, to prove this, we are taking, let v be a any vertices, vertex from capital V, and we will see delta d of v is basically delta of x comma v. Okay. Now, consider a, because there is no negative cycle, so we consider a shortest path shortest path which is denoted by P from S to V. Okay, with minimum number of edges. Minimum number of edges. This is important because we may have cycle. So, this path is simple path, consider a shortest path. So, this P is a simple path. What do we mean by a simple path? So, we may have cycle in the path, but since there is no negative cycle, so that cycle has to be either positive or 0. So, we can just ignore that cycle. So, that means in a path P there is no repetition of the vertices. So, that is possible because we are assuming there is no negative cycle. So, if at all there is a cycle in the path, that cycle could be positive or 0. So, we are talking about shortest path. So, we may ignore that cycle, we will not visit that cycle, we will not hop in that cycle, because that cycle has will not get any benefit to us, because that cycle is either positive cycle or 0 cycle. So, we will just ignore that. So, P, the path P will be just the vertices are distinct. So, there is no repetition of the vertices. Okay. So, let us consider this path P. So, let us write the path P. So, we have S which we are denoting by say V0, and we have V over here. So, this is our path P. So, it may be visiting some vertex V1, V2, V3 and so on, dot dot dot, and this is say Vk. Okay. So, there are say k elements dot 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 v k elements, k number of vertex in the path. Okay. And since P is a shortest path, so what we have? We have delta of S comma Vi is basically delta of S comma Vi minus 1 plus W of Vi minus 1 then Vi. Okay. So, if you take a vertex up to Vi, so this is optimal substructure problem. So, what optimal, in the last class we have seen what optimal substructure problem. If a path is a shortest path of a if P is the shortest path of a graph, then any subpath will give the shortest path of that vertices up to that. So, that is the optimal substructure problem. So, if you take a subpath up to Vi, so that will be the shortest path of that. So, that is basically Vi minus I, that is basically because this is a path, this is shortest path from S to Vi minus 1, and this is shortest path from Vi minus 1 to Vi. So, that means if we sum it up, that should give us the shortest path from, because that is the subpath of this path. So, that should give us the shortest path from S to Vi. Okay. So, now initially, so we are putting initially degree of S is 0. Now, that is basically delta of this S is V0, delta of S comma S. So, S is nothing by V0, delta of S comma V0. Okay. Because why this is true? Because there is no negative cycle. So, what is the shortest path weight from S to S? If there is no negative cycle, then the shortest path from S to S is the best thing we can do, we remain at S. So, that is basically degree of S initialization. This is the initial step. So, this is the initially we have this. Okay. So, initially this is done. So, degree of V0 is basically delta of S comma V0. So, this is done in the step 0 or initial step. Okay. Now, so after one pass, so we are having, if we recall the algorithm, we are having a loop for in the Bellman-Ford algorithm, we are having a loop for 1 to v minus 1, and for under this loop we are checking all the edges and we are trying to relax the vertex v. Okay. So, this loop will start from I is equal to 1, I is equal to 2 like this. So, this is I is equal to 1 means first pass like this, one pass. I is equal to 2 means second pass like this. If we consider like this, so after first pass, what will happen? So, initially this is done. So, after first pass, so after one pass, so what will happen? This is a edge in the graph. Okay. We do not know the numbering of this edge, but this is a edge. So, this edge number will come in some order, because in the inner loop of the Bellman-Ford we are doing this for all the edges. So, this edge will come, this edge number will come in some order, may not be in the first order, first edge number 1. Okay. So, once this edge will come, in that case what will happen? The degree will be d of v will be basically will change, because everything is initialized by infinity. So, degree of v1 will change to d of v0 plus w of v0 v1. Okay. So, this is after first, and this is nothing but what? This is nothing but delta s comma v0 plus w of v0 v1, and from this result this is nothing but delta of s comma v1. So, after first pass this is done, v1 is basically delta of s comma v1, this is done after first pass, because this edge number will come in some order, it may not be in the first sort. So, this edge number, if it is 1, then we are lucky, we just change this by in the first sort. Okay. But we do not know how this ordering will come. So, this is fixed, this is done, after first pass. Now, similarly after second pass what will happen? So, after second pass, so once this is done in the first pass, then the second pass, this is one edge, in the second pass means I is equal to 2, I is equal to 2 we are doing for all the edges again. So, this is one of the edge, so this edge number will come in some order. So, once this edge number will come, then it will do what? It will change this. So, the degree of v2 will change to d of v1 plus w of v1 comma v2. Okay. So, this has to be changed. So, this is basically, now this is already done. So, this is basically delta of s comma v1 plus w of v1 comma v2, and so this is from this theorem, this is nothing but delta of s comma v2. So, this is done after, so this is done after second pass. So, this is basically d of v2 is basically delta of s comma v2. So, this is done in the second pass. Okay. Now, similarly, so suppose our numbering is like that, h numbering, this is number 1 h, this is number 2 h like this, then in the first pass itself it is done. Why? Because first pass, if this is h number 1, so we will start with this h, or if this number is before this, then this is done in the first pass, and then when this edge number will come after this, then this will be done, but we cannot assume now, because this s is v is any vertices. So, this ordering we do not know, it depends how we are numbering them. So, but anyway after second pass this number will come, and when this number will come, this is already fixed. Now, once this is fixed, when this number will come, this will make this fix. Okay. So, this is done after second pass. So, once this is done after second pass, so in the third pass what will happen? So, after third pass, so this degree will change, degree of this will be, so this edge will be, this vertex will be relaxed, degree of V2 plus W of V3. So, now this is already done. So, this is basically delta of S comma V2 plus W of V2 comma V3. Now, again by this theorem, by this result, we can say this is nothing but delta S comma V3. So, this is done after third pass. So, after third pass, after I is equal to 3, this is done. Even this could be done in the first part. If in the first pass I is equal to 1, if the ordering is like this, if this is before this order, if this is after this order, then it could be done in the I is equal to 1 itself. But anyway, we do not know the ordering, I mean how we numbering. So, that is why we have to do like this. Okay. So, D3 will be delta of S comma E3. Now, so this way will continue, and after the kth pass, so what will happen? So, after the kth pass, so this edge will be, if it is not yet relaxed, if it is not yet relaxed and reach to the this final mode, so we have to relax again, I mean it will be get relaxed in the kth pass at least. So, kth pass, if this d of Vk minus 1 is plus W of Vk minus 1 comma Vk, if this is less than that, then we must already the degree was having. So, we must relax this, and this, because this is already done in the k minus 1 path. So, this will be basically because this is delta of S comma Vk minus 1 plus W of Vk minus 1 comma Vk, and this is nothing but d of Vk minus 1 plus, okay. So, now this is nothing but delta of S comma Vk. So, by this result. Okay. So, this is done after kth pass. Okay. So, now, so this is after kth pass, this Vk will be basically d of Vk is basically delta of S comma Vk. Okay. So, now this is the correctness. Now, that is why it is, why the outer loop of Bellman-Ford is 1 to order of V minus 1, because this is because this, so V, we do not know the where is V. So, now how many vertices are, this is a simple path, because there is no negative cycle. So, every path is simple path. So, these vertices are distinct. So, how many vertices we can have in the middle at most? So, there are at most V vertices. So, there could be V minus 1 vertices in the middle. So, every path from S to any other vertices can contain at most V vertices in the middle. So, that is why that the outer loop for the Bellman-Ford algorithm for up to V minus 1, because this path, any part of such P content, the number of vertices is V minus 1. So, that is the reason we run that outer loop up to V minus 1. Okay. So, this is the correctness of Bellman-Ford algorithm. Now, we will discuss some application of Bellman-Ford algorithm, like how to solve the linear programming problem. Okay. So, next topic will be some application of Bellman-Ford algorithm. Okay, so mainly we will talk about the how to solve the linear programming problem. Okay, not the general problem, general linear programming problem, but a particular version of a linear programming problem which is called linear constraint, but that we will discuss in the next class. Thank you.